Good morning, everybody. So it's 11, so we need to start. It's my great pleasure to welcome Jacek Dobaczewski from University of York and University of Warsaw to our nuclear theory seminar. Jacek is very well known in nuclear theory community, but there are some young people who do not remember him because the last time he was here, it was in 2014. It was even before COVID times. So we are welcome him back. So let me say a few words about Jacek. Jacek is a chair in theoretical nuclear physics at the University of York and also professor at the University of Warsaw. He got his PhD in nuclear physics in Warsaw in 1979. And then he joined University of Warsaw in 1980. So there was a very fast track at that time in Poland. And then he became full professor in Warsaw 2002. In 2007, 2017, he was a distinguished Finnish professor at the University of Jyväskylä in Finland. And then in 2015, he transitioned to York as a leader of the theory group in York. So Jacek was involved in many things. I will talk about physics just in a second. And he was head of the nuclear structure theory division in Warsaw, member of the board of directors at ECT Star, okay, and then member of the NAC at INT in Seattle. He was a chair of INT advisory committee in 2003, 2004. He was on the real theory group executive committee and member of the steering committee of talent. So he was involved in many activities which are vital importance for every theory program. He's a fellow of the American Physical Society. He was editor-in-chief of Journal of Physics G between 2017 2022, and was awarded many important awards. So at present, his scientific activity is focused on deriving energy density functions for nuclei. So he pioneered many areas of nuclear structure. He did foundational work on lattice DFT, which is HFB in coordinate representation. He predicted that shell structure of dribbling nuclei will change, okay, as compared to normal nuclei. He made foundational work on collective motion, large amplitude collective motion, and he will talk about also energy density functionals and pseudo potentials today. Welcome, Jacek.
Thank you very much, Vivek. Great pleasure to be here, and thank you very much, Vivek, and the theory group for inviting me. It's a really visit to a friend. With Vivek, we first met in, wouldn't believe it, early 70s, I guess. And then our first paper, I checked that, 1988, not 1888, but 1988. So a lot of
young people at the audience.
yes. So a lot of very nice collaboration, and we are great friends, and we visit each other regularly and intense collaboration on several topics. Today, I'm going to talk about the specific application of nuclear-DFT, which is about how to calculate nuclear electromagnetic moments. And we made the application to heavily deformed and open shell or nuclei, which is the main subject of the talk. So here I listed my colleagues who contributed to the results, which I'm going to show you today. And the person I would like to mention particularly is Hirschegg, who is my postdoc now at York, and whose results I have not been published yet, and I will show them today. So, okay, it doesn't work. The slide changer.
Maybe you need to click on the slides. Mouse.
Sorry?
Click on the screen.
Not on this
Yeah,
one.
okay.
Okay, yeah.
Not down. Somehow it gets to sleep mode after not being used. So that's a bottom line. I humbly learned from Ben Mottelson long time ago that any talk should begin with the bottom line, which the dilemma is the main message. And I think the main message I would like to convey to you today is that this particular observable or set of observables is all about three effects or three elements: polarization, I'll explain what it means, self-consistency, and symmetry restoration. So this will be my first three slides. I will try to argue that these are essential elements of the DFT description of electromagnetic moments, and then I will show you results based on this approach. So polarization, what is this? So we work in the DFT, which resembles a mean field approximation. I will tell you in a few words in the next slide that it is not really the mean field approximation. Nevertheless, the technology and interpretation can be understood in the mean field language. So what is the polarization of an odd particle when you add it to a doubly magic core? So you know that the doubly magic core is a spherical system. It conserves rotational symmetry, but when you add a particle to this system, particular thing happen. Namely, imagine that above the Fermi surface, like in this view graph, there is an orbital which has some angular momentum, and if you apply a quadrupole field, if you add a quadrupole field to the spherical mean field, there is a very generic thing which happens, namely degenerate orbitals, which have particular projections of the angular momentum on the symmetry axis, split. And the direction of the splitting is generic, namely any spherical mean field supplemented by a quadrupole deformation or quadrupole perturbation will result in this kind of splitting, that the orbitals with projections 1/2 will go down on the prolate side. This is the prolate side, namely the nuclei in this direction have a shape of the rugby ball, and the nuclei on this direction, negative deformations, have the shape of the disk. So on the prolate side, the lower projection goes down and the highest projection goes up. Schematically, for any orbital, no matter what is the degeneracy of this orbital, what is the angular momentum of this orbital, it always happens. On the oblate side, the inverse happens, namely this orbital continuously change the position and becomes lowest on the oblate side. So you understand that if you put an odd particle on top of the deformed core, it can go either here or here to minimize the energy. And the result is that it goes to the oblate side. This view graph is not really perfect. This orbital is steeper than the other ones, and the minimum energy is on this side. So polarizing force of an odd nucleon generically is such that a particle added to the spherical core will result in an oblate deformation, like here. This is the picture which illustrates an oblate shape, and the circling particle along the symmetry axis polarizes the system in the direction of the disk. The inverse happens when you dig a hole in the double magic system, because the same rule is valid, namely the highest projection orbital goes up on the prolate side and the lowest goes down. However, now we have a hole. And the lowest energy, this hole behaves like a bubble in the water. It tends to go up, not like here, the particle drags the system down because this lowers the energy. The bubble, the hole, will drag the system up as high as possible. And in this way, a hole in the doubly magic nucleus always leads to a prolate shape. So here you have a hole orbiting the nucleus in the opposite direction, by the way. So you will tell me why the hole, to generate the angular momentum like that, orbits in the opposite direction to the particle, but it does like that. In both cases, the angular momentum is aligned along the z-axis in the positive direction. So these are the rules of polarization in any mean field theory, in particular in DFT. So, of course, these are only the first order perturbation theory results, and nothing is right in physics in first order perturbation theory. You have to iterate these to all orders, and then if you take this into account, for instance, here the particle will polarize the core, but then the polarized core will induce quadrupole attractive interaction. So the particle will go even lower, and vice versa. You will iterate this process. At some point, core will say, no, enough is enough. I don't want to go to higher deformations anymore. You will find a minimum. And that's the self-consistent point in which polarization of the particle is balanced by the core, and then you obtain a self-consistent result. So that's the rule how the polarization works in the mean field. Now, a similar thing happened here for the spin polarization. What I didn't tell you yet about is the Kramer's degeneracy. Every line here is Kramer's degenerate. It is composed with an angular momentum pointing to the right and angular momentum pointing to the left. If you put one nucleon, you have to make a choice. And usually, this choice doesn't matter because this is simply a time reversal reflection, and we always put the particle in the orbital with the angular momentum pointing to the right. Now, this angular momentum contains a spin. Spins interact, spin of the particle interact with the spins of the core. This is an attractive interaction again, and the core gets polarized. So by the self-consistent mechanism, part of the projection of the particle is transferred to the core, and self-consistently again, you obtain a net result in which the projection is partly in the particle, partly in the core, and you have to take into account core polarization if you ever dream about properly describing magnetic properties of the nucleus. And here there's a little detail. We realize this polarization by the spin-spin interaction, which is implemented by a specific object which is called the Landau parameter. And adjustment to data, it's a single parameter we adjust here. This is the value which is adjusted to data. So a very long story here. Let me go to the more brief view graph explaining self-consistency. I already described in words how it works, but in practice, you know very well how the Hartree-Fock theory works. You first of all, in DFT, you map a many-body wave function onto a single particle wave function. So, as I said, DFT is not approximating nucleus by a mean field. It employs a mapping of the many-body wave function into the single particle wave function. This can be done. There are very strong theorems about that. But in practice, what we do, we don't use this mapping. This is a very difficult task now being tried only. This is called an ab initio derivation of the functional, but we usually use phenomenological functionals with which we perform self-consistent Hartree-Fock loop, and that's how we realize this balance between the odd particle and the core. So, and the second element, which I was referring to, is self-consistency, and the third element is here. is absolutely essential to understand that this approach breaks symmetry. And all these states lead to deformed states, and deformed state is not what experiment sees. Experiment is done on the good angular momentum state, and that has to be corrected by the procedure which is called symmetry restoration. In this particular case, I recall here the polarization by a hole, a prolate nucleus with a given projection. The symmetry restoration brings about a set of states which are all rotated about the axis which is perpendicular to the symmetry axis. And you obtain a set of states like that, and you average these states with an object which is called a Wigner-D function. This is not something which is easily explainable, but the analogy with the translation is obvious. In the translation, the wave packet, localized wave packet, doesn't have good angular momentum. To restore good angular momentum, you shift the wave packet and you average it with the plane wave. And the Wigner-D function is simply a plane wave for rotation. So you can see that this averaging, if I use here a unity, the D function which is equal 1, which is a D function for 0 spin, I will obtain a spherical object. The mass distribution will be spherical and there will be no spin. No net spin will appear, and that's how the spin 0 state is obtained by the symmetry restoration. In our case, it is not possible because we have an odd nucleus. Odd nucleus cannot have a 0 spin, and then you have to use D functions corresponding to higher spins, and always they will look like that with, well, it is very difficult to write down this function because the wave functions like that will have many nodes and it's a complicated object, but it will have exactly good angular momentum which we wish it to have. That's the principle of symmetry restoration. Once we have a symmetry restored state, it's a state which is available in experiment, and then you calculate observables for this state, which you can match directly to experiment. So now a few words of explaining the definitions of standard nuclear moments. The quadrupole moment is simply the average value in the symmetry restored state, good angular momentum state, with angular momentum I and the projection I, so the maximum projection. It's a definition. It's a standard how you define object which is called a spectroscopic moment. It's average value in the maximally aligned state of an operator, which is called quadrupole operator, which is written here. It is the sum of the protons only, and then you have this form factor which distinguishes between the prolate and oblate shape. You see, the average value of R squared is 3 times the size in every Cartesian direction. So if you have a spherical nucleus, this is 0. And if you have a prolate nucleus, there is more matter in the z direction, you have a positive moment, and otherwise you have a negative moment. But that's exactly the role of the quadrupole moment, and this is measured. This matrix element influences electronic state, and by looking at hyperfine splitting of the electronic states, you can infer what is the moment of the nucleus. And the same goes for the magnetic moments, the same matrix element, but now for the operator, which is defined as a sum of the z component of the spin and the z component of the orbital angular momentum multiplied by specific numbers, which are called g factors. And these g factors are measured by particle physicists. Every particle has its intrinsic g factor, which relates its spin to the magnetic moment. And here, for the proton, this value is 5.59 with many digits measured, which I don't show. And for the neutron, it's a fundamental number, minus 3.83, and many digits which follow because these are very precisely measured numbers. And for the orbital, you have standard G factors, of course. Proton contributes 1, and the neutron contributes 0. So these are the numbers which we use in calculations. And then we have an operator. Again, we sandwich it in symmetry-restored states, and we obtain a value which is available in the experiment. Now, a few words about the terminology. Intrinsic moments, these are the moments in the symmetry-broken states, and spectroscopic moments I will call moments in the symmetry-restored states, and I will compare both at some point to tell you what is the difference. All right, so this is our playground, and now let's go to specific calculations which we have performed. First, we looked at these simplest systems, namely doubly magic nuclei plus or minus 1 nucleon. So you can add a proton to lead-208, you obtain bismuth. You can subtract proton from lead-208, you obtain thallium, or you can obtain lead-207 or 209 by subtracting and adding a neutron. And you can do the same for all doubly magic nuclei. These are canonical, simplest system to look at the polarization effects. So here we considered 8 different doubly magic nuclei, and then if we have 32 nuclei to calculate, and we can compare with all available data. When we do that, the result is here. So here the plot shows comparison between experimental quadrupole moments and magnetic moments on the left and right, respectively. And the theoretical value is on one axis and experimental is on another axis. So the line, which is tilted 45 degrees, is the perfect agreement line, and the deviations are the departures of theory from experiment. So you see, the quadrupole moments are fairly well described, but there are some deviations here and there, especially for very small quadrupole moments. Here, the quadrupole moments are below 0.2 bar. When the moments become larger, the agreement is visibly better, up to 0.3. But here, next to doubly magic nuclei, the deformations are much smaller than in open shell nuclei, as you will see a bit later. And for the magnetic moments, here is the comparison of the experiment and theory. This line is adjusted to data. The tilt of this line is adjusted by fitting this one parameter I was telling you about a minute ago. And then you obtain this kind of agreement, which I think is not bad. However, this calls for really very good agreement because in this scale, the main factor here is orbital angular momentum, and this is fixed by total angular momentum. So it's not really a tremendous success too. So here I will show you 3 outliers, which are rather remote from this line. And I want to convey a message that the discrepancy of the order of 1 Bohr magneton, this is a unit of magnetic moment, is a significant discrepancy. So 1 magnetic moment discrepancy here, and the fraction of tenths of millibarns is the typical deviation here. So, yes? Yes.
I have already, sorry. Why the average of this? I mean, what is the thinking? Why would you choose to mix such different functionals and take the average?
Yeah, my next sentence.
Oh, sorry.
That's exactly the point here. So you wanted to see what is the impact of uncertainties related to different functionals adjusted to the same data, more or less, because these functionals are always adjusted in a similar way, masses, radii, some observables, which do not involve time-odd properties. And here, what I show are the averages, and the average error here is within the symbol. Only in one case, you see tiny error protruding from the symbol. It means that all these functionals give exactly the same result, and they are stubbornly away from data to this precision. So there is something to be done on the functional level, certainly, or at the level of the methodology, which we use, because you can complicate the state and other effects. I will talk about that in my last slide today. All right, so now let us go to more complicated systems. So here we ventured into open shell, and we did this in the shell between gadolinium and lead, between 82 and 126 neutrons. So altogether, there are 450 nuclei here calculated for 2 intruder states. So in neutrons, we looked at the intruder state, which originates from I13.5, and in protons from proton H11.5 orbital. And I can tell you here, maybe that's a good point to say, that in the history of nuclear structure theory, there were only 2 other papers published which treated these 3 effects at the same level: polarization, self-consistency, and symmetry restoration. 2 papers in the entire history. And if you want to ask why, nobody knows. That's how science takes its mysterious ways, I would say. Simply it was not done. Also, experiment was abandoned. Quadrupole and magnetic moments were measured abundantly across the mass chart. Somehow, this theory was not applied to describe them. So now we have technology to cover vast swathes of the nuclear chart, and we are proceeding slowly, step by step, to do that. This result it dates from last year, and we are going to other regions. I will say a few words about that later. Essential element in doing this calculation here is something which I call a tagging of quasi-particles, because these are all odd nuclei. To calculate an odd nucleus in the DFT with pairing, you do something which is called a blocking. You put a particle with a probability 1 in a specific orbit, and you have to choose which orbit you want to occupy. So this tagging technology allows me to follow a specific orbital from 82 neutrons to 126 neutrons, and I will keep the same structure continuously changing without looking whether it is close to ground state or not. It's a secondary fact, whether it becomes near the ground state at some point and in which point, but this technology of tagging allows me to follow specific state, which is something which is very rewarding, because now I can talk about the structure and not about the uncertainties of where this state is located in energy. And this location is much more uncertain than the generic structure of the given state. So, results. Here is a plot of the quadrupole moments calculated across this shell from 82 to 126 for these particular intruder states. And the important thing to realize here is that here I can see explicitly these rules of polarizations I described at the beginning. For instance, here at 83, the neutron is a particle, right? You have a core, closed core 82, and I add 1 neutron, and this is that's why it is a particle, and polarization is on the oblate side, exactly as I argued in this very simplified first order picture described in the first slide. On this side, the shell is full, and at 125, I dig 1 hole in this shell, and the polarization is prolate positive. Nobody, before doing these calculations, nobody was able to guess what happens in between, and now we know. Namely, this rule propagates to the middle of the shell, So here the nuclei become oblate, more and more oblate, from a fraction of a barn to about 4 barns in the open shell isotopes. And then there is a transition to the prolate side, and nuclei slowly decrease the formation, ending up in these small prolate polarizations next to the doubly magic core. So it's a generic feature of all these results. And if you look at the particular case, for instance, in gadolinum, this transition happens between 99 neutrons and 101 neutrons. So this rule of polarizations next to the doubly magic core is perfectly confirmed also inside the shell. Now, what is not confirmed is the fact that these are not particles or holes all the way across the shell. Of course, here, what I show is the excitation or the energy difference of a given quasi-particle above the Fermi level. So being above the Fermi level, this is particle, exactly as here. And it being a particle, then it changes from particle to hole, and then flips to the other side and ends up as a simple model predicts. However, the place where it happens does not at all correspond to the place when this flips in quadrupole moment occurs. For instance, gadolinum becomes whole around 91 neutrons, and then continues well below this change of quadrupole moment up to 113, where it flips to the other side. So this rule of what does a particle and what does a hole does not expand to the middle of the shell. And again, you wouldn't know if you didn't do the calculations. Now, one slide or two to compare intrinsic and spectroscopic moments, because as I said, in the history of nuclear physics, theoretical nuclear physics, calculations which were using spectroscopic moments or deriving moments were really like rare pearls, which I would like to collect. So if you know another paper apart from these two I mentioned, please let me know. By the way, these papers were one paper published in 2014 by Benjamin Bali from the group of Michael Bender. They calculated one nucleus, magnesium-25, and another one was published last year from the same group by Walters Rissens, and they calculated one chain of indium. That's all. That's really the entire history of this kind of approach. So were these papers which were not looking at spectroscopic moments right or wrong? Here, when you compare spectroscopic and intrinsic, using this canonical relationship, which dates back to Bohr and Moselson's book, where the coefficient here is a square of the Clebsch. In this particular case, it's 55/91. You see that spectroscopic and intrinsic are almost the same, perfect agreement. However, if you use magnifying glass and look at the relative comparison, namely you subtract spectroscopic and intrinsic, or you divide one by another and look at the percentage deviation, then you see that for small quadrupole moments, this rule does not apply. It has been derived for large deformations. It does not perfectly propagate to small deformations. And if you want to remember, what is 5% precision only applies to nuclei with quadrupole moments larger than 1 barn. So all the moments derived next to the doubly magic shell, which I was showing before, require spectroscopic derivation and symmetry restoration. For magnetic moments, I do it with the arrow. Yes. So it's a disaster. It doesn't compare at all. There is no relationship between spectroscopic and intrinsic. This is absolutely mandatory to look at the symmetry-restored value spectroscopic moments if you want to have any connection to experimental data and Well, if you look at the same type of view graph, comparing spectroscopic and intrinsic on the plot, which has this 45 line, I mean, you see that the agreement is kind of correct next to the doubly magic system, but then deviates dramatically inside the shell and then comes back on the other side. So now the most important part, how all this compares to data. So here is a comparison with data of magnetic moments in the top panels, quadrupole moments in the bottom panels for the odd Z systems studied here or odd N systems studied here. So, I mean, there's a very nice discussion about the comparison. Let me start with quadrupole moments. So you see, there are not too many data points. I think 15, well, maybe less here, which are available in the literature. You see that agreement here is perfect, then there are no data, not so good agreement here. Here it's an interesting case, namely, the value was measured, but the sign was not. So experimentalists attributed a large error to this point, but we think that simply the sign should be flipped to the other side, and here it's correct. Now, for these neutron orbitals, the agreement in lead is very nice. Then it's correct here, perfect here, but in Mercury, a disaster happens, namely at heavy Mercuries, the agreement is fine, but then theory flips to the oblate side. So there is something to solve here and explain why this happens in theory and doesn't seem to happen in experiment. For magnetic moments, you can see that here agreement is quite good. It somewhat deteriorates in gold. Then here at one point in thallium, which has been measured, but experimentalists forbid me to show the point in my talk. I'm very sorry about that, but it happens with experimentalists sometimes. They want to publish a Nature paper with this number. In secret, I will tell you that it matches theory quite nicely. And it has the point here was calculated before I knew the experimental point. So, I mean, you could be tempting to say that there is a deviation systematic which increases for heavier isotopes, but then it comes back to the experiment. So, well, no really conclusions can be drawn from that. Now, for the other orbital, here it's quite good agreement. Then there is a problem with Mercury related to different shapes. And then there is this kind of agreement or disagreement between experiment and data. I must say that experimentalists still debate the way to extract moments from hyperfine splitting measurements. So there is still uncertainty here related to the model dependence of the link between measured hyperfine splitting properties and nuclear moments. So the jury is out. I mean, maybe the values here will change. In particular, some of these papers publish two sets of values which are slightly different beyond the experimental errors they cite. All right, so this is this region. Now let me go to the unpublished results by Hirschegg. What he did, he covered this set of nuclei between tin and gadolinium, so shell down in protons, and then again I will show you only comparison with experiment. For instance, for the quadrupole moments, again the agreement is I would say quite spectacular. Remembering that here there is no parameter because this one parameter which we adjusted does not impact time event property like quadrupole moment at all. So this is really a no parameter calculation. Of course, as you know, when someone says no parameter, there are always parameters hidden, but at least they were not adjusted for the purpose of this work. These were adjusted by Vitek and collaborators 10 years ago. This is the functional UNIDEF1 which we employ in this study. And then for G7 half here, we have results here. Here, again, there is a marked deviation related to different oblate or prolate structure. And here we have an oblate structure, so we can have another point here. Simply the transition from chlorate to oblate happens probably one isotope too early. And in this other intruder orbital proton H11 the agreement is also quite nice. I must say here, these are all data, the new data aligned with theory better than shown here. For the magnetic moment, the story is mixed. For the intruder orbital, it's not bad, I would say. Again, here, there is no place for readjustment of parameter because here it's perfect. So there's no way we can try to move these points up and down by the spin-spin interaction. Here, it's a different story. There is a marked difference for this orbital, which is not intruder, and this is the point which we have to study in details. If I wanted to be spectacular, I would say here it's a physics beyond standard model. This model I described is standard, and there is some other physical element which is missing, which we have to identify. All right, now the last thing I want to describe today is the problem of so-called effective G factors. This technology or approach was popular or still is popular in very many branches of nuclear physics, which calculate magnetic moments, especially when the approach does not have large valence space, like shell model, which is reduced to a tiny region around the Fermi surface. Then to get agreement with data, very often theories, after spending a long time in diagonalizing large matrices, they multiply the final result by a number to get closer to the experiment. So we try to test that, whether this approach is needed for the DFT or not. What is shown here are these effective G factors derived in the following way. For every nucleus, I plot effective G factor which would be required to bring theoretical results exactly to the experimental point. So here the distribution of these calculated effective G factors clearly points to the value 1, so we don't need it. And the reason is that polarization in DFT acts in the humongous single particle space. If we use 20 shells of harmonic oscillator in our space, the polarization is acting in this full space. If the space is cut, then this value probably cannot be obtained in this way. And you also see these 4 outliers I referred to in the beginning, and they do not really match this trend. If I wanted to use effective G factor of 0.5, that would be completely out of this world for bismuth. So this is not really a meaningful thing to correct the value of the magnetic moment here and bring it closer to data. So, future, okay, here. How to proceed? So, of course, I have to make strategic choices where to go from this point. Of course, we can cover the entire mass chart with that. We are going slowly, step by step, doing that, but probably we should also start thinking how to correct, how to make this better, because this is something which really lacks precision in some specific aspect. So here I list a few developments which can be done. We can work with more advanced functionals, and I think this is something which I'd be very much interested in, and we, with our collaborators, Karin Benasser and Markus Kortelainen, we work in this direction intensely. Octopole deformation, I tried, it doesn't seem to be bringing interesting or useful result. There are some subjects which could be tried with some priority to look at triaxiality. Herlich will look at triaxiality. As we speak, he's doing that. Configuration interaction, and we take a few orbitals and mix them. K-mixing, namely mix different K values of orbitals not the one which I was describing, but take all of them and mix, and then you can use quadrupole, octuple collectivity when you take a full collective space. All these are standard nuclear structure elements which could also impact magnetic and quadrupole moments. And then there is something which, again, with Herlich, we work now very intensely, namely implementing the two-body meson exchange currents. And this is something which is very promising. If you ask me a question in the discussion, I can show you why. But apart from that,
Jacek,
that's all.
what is the color scheme? Some of those are green, some of those are red. The happy face.
Happy face, which I like very much, and red I don't like because I won't do that at present. All are happy because I didn't have a font, which goes. So I represented it with colors. I thought you would figure out. Yes, so it is happy but very angry. Thank you.
Beautiful talk, really impressive. The question is, in the cases where the dipole, the quadrupole, come in, where the predictions are off, are the other observables good, like the energies, the spectra, the object, do they look okay, or are they also off?
These observables belong to the other world, time-even world, which has been adjusted, and the agreement or disagreement with data is known. It agrees usually quite well, but there are deviations, known deviations. However, magnetic properties are rather independent of that. There is some link, but they probe different part of the functional. So I think this question can be looked upon separately. I mean, time-even observables and time-odd observables can be evaluated separately.
Jacek, could you go back to your happy faces? Yes, so in some calculations, right, you employ angular momentum projection.
In all of them.
In all of them. So, but in what sense then K mixing is a separate entity? Because when you do angular momentum projection,
Yes.
you have to sum up over all K values.
Yes, yes. So that's a very interesting question. It is true that at the spherical point, all K components or all omega components carry exactly the same information. So you mix them or not mix them, it's the same. At the low deformation limit, you have split orbitals, and you can project the same total angular momentum from every one of them and mix them. In principle, this should not change too much, but it has not been done. So you will see whether this kind of mixing maybe a little bit corrects the result or not. And then there is a strong coupling limit, very large deformation, in which K mixing would not make sense because these K orbitals are really split tremendously in energy. What can be done, it's another, I simply call it another name, I call it configuration interaction. Mixing of orbitals, which do not originate from the same spherical orbital, but they are nearby one another at the surface, and they can be mixed in principle. Again, by technology which is known, but we didn't employ it yet.
So, calcinic, the red phase here.
Yes.
Octopole.
Yes.
So when you have nuclei which have stable octopole deformations, of course, then the effect of octopole deformation on magnetic moments will be incredibly large.
Absolutely, and it is, yes.
Because then you have parity doublets,
Yes.
and they have basically the same magnetic moments because they have the same intrinsic structure. While at the limit of beta 3.0, right, those will be completely different orbits.
But we can discuss that. The red phase is based on some calculation, which shows that the parity doublets, at least in vibrationally octupole octuple vibrational nuclei are different magnetic moments. So, but the one which is correct, namely the parity, which is component to data, is not really affected too much.
So I got. Thanks, Jacek, for a very nice talk. So I invite the bullets. Could you comment on the meson exchange curve? And how would you ensure that they are consistent with the renormalization in a way that doubles the correlation in the density function?
Thank you very much for this question. I didn't ask you to ask the question, but I want to answer it because that's something which is very promising. Sorry. So all what I know doesn't come from myself. It comes from Takayuki Miyagi. In January in Hirschegg, he showed this slide where he included two-body currents in ab initio calculations, which probably are perfectly correct from this point of view, which you mentioned, and without any parameter, he obtained, this was his previous result here, which we published in Nature, which was deviating from experiment quite substantially, but with two-body currents, his number is right on top of that. So that's extremely encouraging result. Now, in January, I asked Takayuki, what about other nuclei, not only indium? And last 1 month, we met in New York, and he brought a whole spectrum of results, including bismuth 209. This outlier, and right, it goes top to the data without any parameter adjustment. Extremely encouraging result. Now, what we can do in DFT is implement the same two-body operator. Okay, and of course, I fully appreciate your compatibility argument, but well, before we implement it, we will not know whether this plays also a significant role and whether it works differently.
Jacek, thank you as well as everybody with the talk for taking the time to give the intuition. It was super good. My question is on, you mentioned that many of your predictions didn't use parameters in the sense that you didn't adjust new parameters. You just use parameters of unit one. I'm thinking that since many of these observables are very sensitive to phase transitions in your nucleus, going from prolate to oblate or vice versa, could it be that just a small change in the parameters, not affecting the other properties like masses and radii, could shift where that change happens in such a way that it agrees better with data? That's what I'm thinking. And the question is, have you considered, or do you know if anybody's considering readjusting slightly some of the parameters you need to fit this type of data?
Well, certainly readjustment taking into account these fine spectroscopic properties is called for. Unfortunately, what DFT exploited probably or reached the limits of how this can be corrected for observables which were taken into account. So if you add another constraint or another request to the same functional, well, maybe you will be having hard time to correct it because the other observables will still be stubbornly dragging to the standard place. So I think this program can be realized once we have richer functionals, more advanced functionals. And there is quite a number of ideas what to do, higher order derivative terms, finite range, I mean, all kinds of things are tried. And then once we have this implemented, we have already preliminary results in this direction, but they are not worth employing in this massive calculation yet. But if these functionals are adjusted, then we will take these tiny properties into account and try to describe more observables in the time given set. So,
but of course, you know more than me about this. I just think that since this is such a sharp transition, it might be that how you lost that the change in the parameters is very small for a big effect in this observable, so
Absolutely.
that you don't compromise the other properties. But who knows? Maybe the ways to.
Yeah, but you see, we work with this functional for quite some time, and we know that it should be corrected in many other aspects. For instance, spin orbit. Spin orbit splitting has only two parameters in this functional, and it's probably too poor parameterization to describe fine details of the spin orbit splitting partners in different regions of the mass charge. And we see that clearly when I do calculations in the region of tin, then clearly the orbitals are 1 mega electron of experiment, which is clearly the spin orbit effect. So there are, I would say, more urgent things to consider first, but all of them should be considered once we do the final adjustment of the function.
Thank you.
Okay, so I haven't seen any questions online. Let's just conclude this and say speaker.
Thank you.